Bueno, aquí conozco, en este momento se encuentra el doctor Camilo Zamora Ledezma. Eh, Él es un físico experimentado con doctorado en tutela por la Universidad de Nanterre de Francia y la Universidad de Central de Venezuela. Tiene una amplia experiencia como pesquisador y profesor en instituciones renombradas como la Universidad Central de Venezuela, Instituto Venezolano de Investigaciones Científicas, también de Venezuela, o Politécnico de Montpellier, Francia, Universidad de Bordeaux, Francia, también tiene experiencia en Ecuador, y en la Universidad Católica de Murcia, en España. eh, Cabe calentar que es un pesquisador bien internacional, con experiencia en diversos continentes, como podemos apreciar. O seminario de hoy que o doctor Camilo estará ministrando es sobre desenvolvimiento, caracterización y aplicaciones de cerámicas avanzadas de alumina con fases alotrópicas de carbono. De esta palestra se discutirá el desenvolvimiento a caracterización y las aplicaciones de cerámicas avanzadas de aluminio reforzadas con allotropes de carbono, específicamente nanotubos de carbono y grafeno. La palestra aborda desde síntesis hasta los métodos de procedimiento, enfatizando las técnicas de dispersión y sinterización. La caracterización realizada en los composites revela propiedades mecánicas aprimoradas en comparación con alumina convencional, apoyadas por análisis microestructurales y testes de resistencia y conductividad. El indicio también es demostrado su potencial en diferentes áreas, incluyendo, entre otras, a bioingeniería y a biomedicina, destacando como estas propiedades exclusivas pueden ser traducidas en innovaciones tecnológicas. La presentación también nos mostrará dos seminarios o desafíos que se tienen en esta área de pesquisa. Entonces, vamos a iniciar con el Camilo, que sea Dalle, para iniciar.
Vale, gracias. Thank you. Juan, I'm going to talk in English, so I will try to do this slowly, so they can understand my seminar. Thanks for the introduction, for the invitation. For me, it's always a pleasure to be to have this opportunity to show what we can do in our research group. So thanks, Juan Carlos, for the invitation. And I am so glad to be here, and I hope this is the first of many future interactions. Okay, as the professor mentioned at the beginning, I try to summarize the outline of this presentation as follows. First, I want to talk for a few minutes about the university I'm working right now here in Madrid, in Spain. Then I will make a very rough introduction regarding nanomaterial, bioengineering, and biomaterials. This is also because my research group is a multidisciplinary research group with the main focus on bioengineering. So this is our main research topic I related with the regenerative medicine and bioengineering, but also we work a lot with nanomaterials and biomaterials. Then I will present today a few of the works we have done the last 5 years regarding the fabrication of ceramics using different type of carbon allotrope as graphene and carbon nanotube, and the most recent work in which we avoid the use of these nanoparticles, but instead we have fabricated a new material for biomedical application, okay? So just a few words about the institution I am working right now. I am working in the Universidad Alfonso X el Sabio, which is the main campus are in Madrid. We are located in Madrid, in Spain, okay? However, we have three main campus. In Madrid, we have two campuses, one in Chamberí and the other in Chamartín. But all concerning bioengineering, biomedicine, and medicine is located in a small city, which is outside Madrid, which is called Villanueva de la Cañada. So it's around 30 kilometers away from Madrid. Also, this is one of the biggest and oldest, the first private university here in Spain. And also now we are opening a new campus in another community, which is located in Malaga, and is expected to get around above 3,000 students. In order to provide few numbers about to have an idea at a glance of the university, we have several students. Today we have, according to the report 2023, we have around 14,000 students, and we have several faculties. I am located in the higher polytechnic school, but we have veterinary, we have medicine, we have education, ontologies, we have even arts and music faculties, okay? So first off, I wanted to start this talk introducing the nanomaterials. Perhaps I prepared this exposition more thinking about the undergraduate and master students. So I'm going to mention just a few general words about nanomaterials. As you might know, nanomaterials are very interesting and they have been used before the last 50 years. Overall, the last 20 years, we have a lot of interest, growth in this area because many issues. And I just wanted to start by defining what is a nanomaterial. Typically, a nanomaterial is defined as a material in which at least one of their dimensions are between 1 or below 100 nanometers. Everything below 100 nanometers are considered like nanomaterials. In order to have an idea, if we look at the graph, for instance, if we have, I don't have here, but typically cells are around 1 to 10 microns. A hair, it's around 10 microns, 100 microns. If you go down in size, you can go to the nanomaterials, such as those we are going to talk today, like nanotubes, carbon nanotubes. They typically has a very narrow diameter, around 0.7 to 1.5 or a little bit higher in nanometers. Okay, so this is just to have an overview about the size. It's very important to mention that a nanomaterial can be if you have, for instance, like in the case of carbon nanotube, you have a microstructure which itself has nanometric dimension, but also you can prepare something that is called in English composites, made of different materials like metallic, ceramic, or polymers. If you combine this raw material with any particles with nanometric dimension like nanoparticles, like carbon nanotubes, your final composite is also called or named nanomaterials. So why we are interested in nanomaterial? Typically, they can provide many benefits. For instance, you can have several enhanced properties, such as the mechanical properties like the strength. If we compare to, I have a message here, maybe. Pardon, sorry. Sorry. Okay, you have also, you can improve the electrical conductivity. They are very versatile. You can put fabricating materials for one specific application. And it has many applications in different industries. And I'm going to focus today in those regarding the bioengineering application, okay? I just wanted to mention also that the main structure you can find as nanomaterial or nanoparticles are those that I try to cite here. You can find typical structures like a 1D, 2D, or three-dimensional materials in the form of particles, tubes, carpet, fibers, like a metallic nanoparticle, gold nanoparticle, iron nanoparticle, silver nanoparticle, etc. Also, I put here the most used low-dimensional materials such as graphene, carbon nanotubes, fullerene. All these three are known as carbon allotropes, but also you have other 2D materials like mexines, clay, silicon, etc. that are also very, very interesting. I now wanted to introduce very quickly about what is a biomaterials, bioengineering, and the question I try to respond each time is how or what a physicist, which is the position, which is the position, or why is you can have in a bioengineering research team a physicist, for instance. So typically, by definition, the bioengineering is the application of engineering principles to the field of medicine and biology. So typically, you are willing to solve problem, offering, of course, environmental solutions. You can also participate to designing medical device or equipment such as diagnostic equipment. You can also participate in the development of new pharmaceuticals, etc. Bioengineering also deals, for instance, with applying biological techniques to modify organisms, such as the genetic engineering. And of course, it is a combination between many disciplines or sub-areas like biomechanics, bioinformatics, biotechnology, and tissue engineering. And then within this bioengineering, we have an area which is focused on the development of functional, from the biological point of view, functional materials. These functional materials from the biological point of view are usually known as biomaterials. And at the same time, they are defined like a substance, which is typically engineered to interact with biological system for medical purpose. This biomaterial can be natural, metallic, can be natural or synthetic, as I mentioned. Typically, at in the current days, the most materials in biomaterial field are called composite because it's the combination of different either precursors like metal, polymeric, ceramics, or nanoparticle or bioactive molecules. And typically they are known as composites. They are used in different applications like implants, prosthetic, in drug delivery system, and in tissue engineering. So to summarize, the bioengineering is like a point of convergence in different fields of physics, medicine, biology, material scientists, etc. So if we keep this in mind, our main goal in our research group is to be part of a multidisciplinary groups or work team in which our job is to produce materials for one specific application. In order to fabricate this material, we have several routes we can use, and we use this in different projects we are currently developing in our group. For instance, we can prepare materials using electrospinning, either 3D printer or 3D bioprinting. We can use other more simplest technique like spin coating, deep coating, hydrogels, etc. I wanted to stress that today we are going to present some works related with ceramics, and these ceramics are produced by a technique which is called the sol gel technique, which is a very nice alternative to produce ceramic composite materials, okay? So in our current research, we, as I mentioned, we form a part of a multidisciplinary research team, and we focus on produce material for specific application. Currently, we have indeed working in more projects, but we are working in 3 different projects, which one of them is related, for instance, with the development of novel titanium alloys for implants or prostheses. We also are working with the colleagues from University of Sevilla in the development of novel ceramics for bioapplication. And also we are currently collaborating with a few institutions in order to produce composite based on polymer by using electrospinning, 3D printing, and drop cast hydrogels. For this, we use different bioactive materials and bioactive components, and also we use different precursors. As far as ceramics are concerned, I just wanted to stress that ceramics are a very, very old subject for material scientists. If we look at the book, you can find a very old, ancient pottery, like this I show in the presentation, which is 25,000 years old pottery, which is a baked clay found in Czech Republic. So it's a material which has been used for a long time. And in the last century, the application has been increased, okay? And overall, the last 10 years, there are a lot of interest in developing novel ceramics, composite biomaterial for many applications, but overall, those focus on novel biomaterials or for the rocket industry are very interested in this type of material. And maybe the question will be, why ceramics are very interesting for different research topics? I think it depends on the application, but every research will conclude that one of the potential that ceramic has is that they have a very good mechanical properties. So this is a typical plot in which we have, you find the mechanical properties of materials, specifically the Young modulus, and you have the different materials. For instance, if we go from bottom to top, we have, for instance, the polymer growth, polymers, natural, composite, metal, and then we have a steel. And if we look at here, the plot, we have a very nice balance between mechanical properties and fracture toughness. I will explain this later. So I think this is the main reason why ceramics are really interesting as material, as they are a very tough material. However, depending on the application, this toughness can be a problem. I will try to explain this later. Unfortunately, ceramic also has the main drawback regarding the use of ceramic is related with their brittleness. So this is a material that is very hard, but it's very brittle. So we need to play with different techniques in order to keep the desired mechanical property of the material, but avoiding as far as we can this undesired property, which is the brittleness of the material of the ceramic. One of the routes, according to the literature, we can overcome this problem is to use a technique which is called typically reinforced. So the idea is to reinforce the ceramic using different guest molecule. Like today, I wanted to talk about the use of graphene or carbon nanotubes as reinforcing phase. But the idea is the same that you can find, for instance, in mud bricks, in which you use small spike-like molecule or also is the same that you found in nature, like in nacre. So the idea is that you can put some molecules inside that help to avoid this propagation of the fracture within the material. So if you are able to control this fracture propagation in the material, you also can control the mechanical property of the material. Another problem where it's important to mention that when you try to prepare new ceramic composites, if you look at the literature and you see what has been published on mechanical properties, for instance, in carbon nanotubes or carbon allotropes, you will find a diversity of results in which some of them say that if you put some carbon allotrope, you indeed reduce the mechanical properties. However, you can also find a very nice example in which you can improve a lot of the mechanical properties and other properties of the ceramic in general. So this is a current debate, and that is why I think we have an open window here. So there are many things we can do. So typically, the idea is to be able to produce ceramics with enhanced mechanical properties, but also to find a balance between their mechanical properties. And for instance, in our case, we are really interested in to control the biocompatibility of this material. So we need to try a balance between their physical-chemical properties and the biocompatibility. So when you try to reinforce ceramics with carbon allotrope, you will face several drawbacks. For instance, one of the main problems is how you are able to control the dispersion and the homogenization during the fabrication. This is a huge challenge because once you try to disperse these phases within the ceramic matrix, they are a natural trend to produce small bundles, and these bundles typically they make they can produce a reduction of the mechanical property. Also, how is located the phase, the guest phase is going to play a crucial role regarding the mechanical properties. For instance, if you have intergranular location, indeed, this location might not be the most effective for the reinforcement. So typically, what you want is something that is called intragranular reinforce. So you can provide in that way a better reinforcement for the material. Also, if we look at the problem from the chemical point of view, perhaps another important issue we should overcome is the insufficient bonding between the matrix and the carbon allotropes. So this is more or less, this is a project which was found a few years ago, 3-4 years ago. And actually we tried to address this problem, the dispersion, and the location of the carbon allotrope phase. So as I mentioned, typically the most typical or the most easy way for when you mix carbon allotropes with ceramics, overall for alumina ceramics, is that they are located intergranular. So this decreases the properties. However, we already proposed at that time to produce an intragranular reinforcement in order to improve the mechanical properties. And this is the main goal of this project. So we control the location of the carbon allotrope phase, and also we control the solubilization. Here I just wanted to review quickly how are the different routes you have currently in order to solubilize nanocarbon allotropes. So typically you use organic solvents, or you can use some chemistry, so you can apply some redox function or redox process in order to produce materials that are spontaneously soluble in, for instance, in alkali compounds or alkali solvents. You can also produce an acid functionalization using acid, and you can create in that way, you can put some COOH groups on the carbon allotrope surface. So in this way, the molecule are more hydrophilic. And also you can use typically the combination of different surfactants. These are more or less the different ways you can use in order to solubilize carbon allotropes. So the ceramics we are going to present in the next slide are produced by sol gel. Sol gel is a very common technique that is used to produce ceramics. And in this case, we mix typically a solution which has the silica precursor, and we mix together with another solution in which we previously dissolved the carbon allotropes. So this is a draw in which we are trying to guide you how is the material fabrication. So typically you have a sol, it's called actually a solution, which is called the sol. And this sol is typically based on boehmite. This sol can be also, depending on what you want to do, you can also improve. We also prove this. You can improve the process by adding some seed of alumina. And then in a second step, you can add the carbon allotrope, and then you can mix using ultrasound. Then you can control the gelation, adding some base like NaOH, like sodium hydroxide. You can create the gel, then the gel is dried using an oven, and you produce something that is called the serogel. This serogel is mortar and sieve. Then you apply a technique that I'm going to explain later, which is called SPS, spark plasma densification. Is a process in order to densify, in order to produce the ceramic. So this is the typical process we use to produce this kind of ceramics. So I'm going to present quickly two works we have done. This was the first work we did. We started by doing this mixture using multi-wall carbon nanotubes. So you take the boehmite salt, you prepare the serogel. Once it's dry, it's called serogel. And we were able to identify this combination of boehmite crystal with carbon nanotubes. If we take this powder and we bake them, this, let's say, small crystalline start to transform to something that can be observed like a big grain like this, but still you can see upon calcination, you can see that we have still this intergranular connection between different grains. And this is what we were looking for. So we were aiming to produce materials in which the carbon allotrope is not located at the border, at the edge of the grain, but instead is in an intergranular position or location. So the sintering, as I will explain here, is known as spark plasma sintering, and is a typical technique which is used to densify ceramics. So typically you use this technique, which is it's a very big machine, because you need to combine a high pressure and a high temperature. In this way, by combining high pressure and high temperature, you are capable to compact the powder, to remove the empty space between the different grains, and to reduce the porosity of the material. So you are densifying the material. And it's a really tricky technique, because depending on the temperature you use during the heating process, or depending on the temperature you use during the cooling process, depending on the temperature you use during the, let's say, how the name in English, the threshold, in order to produce the ceramic, depending on the time you spend at this temperature, You will change the grain morphology, the grain distribution, and you, of course, will change the final performance of the material. So it's a really, really complicated technique. So, however, it's the one of the most used and powerful technique in order to produce ceramics. So, as we identify during this project that we have several factors affecting the ceramic fabrication, prior to use this, prior to the sinterization and during the sinterization. For instance, before I already mentioned that we have key parameters like the nanocarbon allotrope dispersion play a crucial role in the final performance of the materials. The presence of or not the presence of alumina seed also play a crucial role. The boehmite at the beginning, the size of the boehmite grains before the annealing is also important, etc. And the SPS, as I mentioned, the temperature, the presence, the annealing time or the temperature ramp will play a crucial role during the preparation. So we need to prepare a pool of different samples. We are talking about for this specific work, we have done like, I don't know, 30, 60 different samples in order to change temperature, the cooling or the heating temperature, the composition, etc. And then we reach some, let's say, formulation with the best parameter. So in this slide, I try to show you what happened then once you have the material. So first, as I tried to explain at the beginning, we are capable to produce the powder. This powder is transformed into a ceramics via SPS. And then we need to take this material, we need to rectify, we need to cut, we need to put into a resin and polish in order to perform all the characterization. Overall, the mechanical characterization. In the first work, we were working with the multi-wall carbon nanotubes and alumina as precursor. So we use different techniques in order to identify that we have the alumina in both cases. So as you can see, here is the XRD patterns, which are capable to identify the different phase in the materials. If you look at from the bottom to up, in the bottom part, you have the multi-wall carbon nanotube diffraction pattern. Then you have the boehmite patterns. Then once you combine these two materials, you can still identify the boehmite, and it's very hard to identify in this the multi-wall carbon nanotubes because it's less, how to say, the carbon nanotubes are less sensitive to XRD. So that is why we decide to use another technique, which is widely used in carbon allotrope called Raman. And in the Raman, using this Raman spectroscopy, we were able to monitor the presence of the multi-wall carbon nanotube in the different stage. In the powder, as you can see in the bottom part, then you can see that we can follow the presence of the carbon nanotube during the annealing, and also after the annealing, once we have the alumina, we are also able to identify also the alumina and the carbon nanotubes. When we work with ceramic, a very important parameter is their density. Indeed, typically within another parameters. The density is one of the parameters which is a very important as they define the mechanical properties of the material. So maybe it's very intuitive, but the material will be hardest as the density tends to 0, or you have no porosity. In this case, we have a porosity less than 10%. However, this 10% for a ceramic can be a very huge if we look at their mechanical property. Non-obstant, in our case, we were interested in to find a balance between the mechanical properties and for instance, their final functionality. And we were, let's say, happy with the result in spite we were unable to get a full dense material, we obtained a material with 90% of density and with nice mechanical property, as we will see next. So then we apply a different mechanical property characterization like hardness beaker. We obtain the beakers hardness around 8 gigapascal for all the composite. It's a very common technique. You apply some indentation. And we did the mechanical property from the macroscopic point of view using beakers, and also from the nanoscopic point of view using Berkovich nano indentation. It's the same technique, but with a different scales. So in both cases, we obtain a very interesting hardness. If you see up to 2% in carbon nanotube, we are obtaining a hardness like is very similar to that of the material without carbon nanotube. So we believe that we were incapable to improve dramatically the mechanical property. However, we observe a small reinforcement in the material. And also, it's worth to mention that another technique is very used for mechanical properties is to see something that is called the fracture toughness, and also if you are capable to measure how is the crack propagation, you are capable to provide the mechanical property of the material. So we have done this with this material, and here we did two different ways. In the plot, in the top part, we use typically the Kc parameter. The Kc parameter is the parameter which provides an idea about the fracture toughness of the material. And in this case, we use the Young modulus, which is from the theoretical Young modulus. So we take the Young modulus of alumina, and we take this value in order to compute this fracture toughness. However, and you see the value is almost constant. However, in the bottom slide, in the bottom graph, we have done the same calculation, but in this case, we use the Young modulus calculated in our previous experiment in the nano indentation. If we do this, so if we use our own Young modulus from alumina, we here note a very nice increase of the fracture toughness with this, which is a very encouraged result. And then we also were capable to produce this different type of microscopy using a scanning electron microscopy, in which we were capable to identify few carbon nanotube which serve like a bridge, and actually we attribute that the reinforced mechanism in this case is through one intergranular connectivity, and also this is the way as the material is going to be is being reinforced. So I just wanted to move to the other work. We have done more or less the same, but in this case we changed the carbon allotrope. We use graphene instead of using multi-wall carbon nanotubes. So this is a typical picture of the graphene flakes. We do the same, but also we change some parameter in order to produce more performance material. And for instance, in this work, we have done a calculation regarding, for instance, we change the concentration of the graphene, and then we see how the distribution of the graphene and also the grain are changing according we change the content of graphene. For instance, if we look at this plot, we have done for different graphene content from 0 to 6%, and also we evaluate the grain size into different location. Those grain located in plane configuration and those located in the cross-section location. And as you can see, typically, there are a kind of natural trend to reduce the size of the grain as a function of the content of graphene. And from the mechanical point of view, what we expect indeed is as you increase, as the size of this grain decrease, this grain in the ceramic, if we decrease the size of this grain, is expected to have an impact in the positive impact in the mechanical properties. As you have more boundaries, you have more grain per unit area, you will have more boundaries and you will have more space for the fractures to dissipate energy. So if you have a big grain, a fracture will be more easily transmitted, okay? In this case, we have done we also use a Raman. We evaluate, for instance, the solubilization of the nanomaterial within the composite. And we use, for instance, Raman. In this case, the darkest point indicate that you have a more concentrated zone with more graphene. However, generally, we find through this technique, we find that our material were really homogeneous. Then we have done the same. We did the nano indentation. We have done this with the same machine, and also we are capable to make this plot. And unfortunately, as we have seen here, for some of the sample, as we increase above 3% of the content of the graphene oxide, in this case, the toughness, the hardness of the material became soft, so we decreased the mechanical properties. However, we were capable to report a window between 0 and 2-3% weight percent in which you can prepare materials using graphene with nice mechanical properties. Here, we also find the same if we use the macroscopic hardness using, for instance, Beaker hardness. We can observe at the cross-section you have a significant difference between the hardness for those samples below 3 weight percent in graphene. So this is a nice result. Also, we reduce the fracture resistance, as we can mention here, and also this is a very interesting property. Finally, in the last minute, I just wanted to mention that all this work has provided to us to find a nice recipe in order to produce, for instance, alumina ceramics with enhanced mechanical properties. So then we wanted to apply this to the bioengineering field. Indeed, we wanted to apply this for the construction of a porous construct for application as human cortical bone replacement. So to summarize, basically we prepare a material like this in which we were capable to combine with other ceramics. In this case, we combine alumina instead of combining with carbon nanotube, we combine with wollastonite in order to produce, in this case, we wanted to produce a porous structure. We didn't want a dense product. And we try their biocompatibility of this material, and we have a very nice result. So here I just show you, once we use the same methodology in order to produce the ceramics, then we have done the structural characterization using the same technique, scanning electron microscopy, X-ray diffraction. And here I really like this image because we were able to use computer automated image, CAD image, so you can have the 3D image of the material in order to, for instance, to provide the porosity of the material, and we were capable to said that in this type of material, we have an open porosity, interconnected porosity, which is very, very beneficial for biomedical application, because this porosity, for instance, allow the fluid to flow within the materials, and this is very good, for instance, to allow the cells to proliferate, to be to differentiate in the, for instance, in bone cells like types. Okay, and then we did few characterization. For instance, we characterize the mechanical properties as the Young modulus. We also characterize the compressive strength. We apply a uniaxial compression, and we were capable to measure the mechanical property of the material. And once again, we make a different sample, a different content of wollastonite. And once again, we find that the best sample were at lower content of wollastonite. In this case, the most interesting sample were those are named AS20, and I will explain this later. So one of the main problem with alumina, if you discuss this with the people who used to work with biomaterials, most people working with biomaterial may say that alumina, indeed, alumina is considered like an inert ceramic. However, if we apply some small surface treatment, or we combine with some specific bioactive molecule or with other precursors, we can transform this alumina into a non-inert. Instead, we can have a bioactive alumina ceramic composite. So this is the key point of this work. We wanted to transform this inert alumina in some bioactive alumina by combining with wollastonite. Also, after the fabrication of the ceramic, we have done a surface treatment by doing some acid treatment in order to create this functional, from the chemical point of view, functional groups. And this composite finally was really capable to produce, for instance, the deposition of this small layer that is called hydroxapatite, which is typically called as the bioactivity. So typically, this is experiment we do in our laboratory. We sort this material into a buffer, and we measure the capacity of the material to create this rich, a layer which is rich in calcium and phosphorus, which is called the hydroxapatite. And as a function of this layer of calcium as phosphate, we can say if our material is more bioactive or not bioactive. So typically, if you put a typical ceramic, alumina ceramic in this buffer, this ceramic doesn't react with the medium, so you are not capable to produce any deposition of this bioactive layer of calcium and phosphorus. On the contrary, in this case, we were able to produce this layer during 5 weeks or 9 weeks, which means that this material is really a good candidate for biomedical application. Further, we have subject this material to be in contact with cells, which are typically human cells, which are called bone marrow mesenchymal stem cells, typically cells that are used for this type of experiment. And we try to see if the cells are happy when we put cells in contact with the material. So we evaluate basically if the cytotoxicity, the cytotoxicity of the material, and then we evaluate also if they are capable to promote the proliferation of the cells, the adhesion and the proliferation. And this is what we have done here using fluorescence and optical density. We use typical assay, which are called viability by MTT. And also, I think here is cellular proliferation activity. Okay, we use typically a Lamar blue, or we just count cells. And what we found, if we compare our samples with the control, so without the wollastonite or the functionalization of material, were not cytotoxic, and also they produce a better adhesion and proliferation of the cell. So to conclude, I just wanted to mention that the ceramic based on alumina are really nice and versatile material for produce material for different applications in the industry and overall in the bioengineering field. We need to face many issues like the dispersion of the phases, their physicochemical property, and the biological compatibility. And remember that we need to find an equilibrium between their physicochemical properties and the biological compatibility. Also, in all the case presented today, we were capable to produce, I call this like a belt or a zone in which we have the best recipe in order to produce ceramic basic composite using nanotubes, using graphene, or without any of these carbon allotropes. As we have shown, the alumina enriched with the wollastonite or with some functionalization show a very nice bioactivity and biocompatibility when we do some experiment with cell culture with mesenchymal stem cells. And the future direction in our case is when we are trying to tune these properties in order to produce, for instance, bilayer or multi-layer scaffold to produce tailored material for biomedical application. Then I just wanted to share with you some of some recent special issue. We are open to receive any submission. If you have any article in this area of bioengineering, biomaterial, please, you can reach out to us in order to submit the paper. And also here, I wanted to thank also my collaborator, of course, you for your kind attention. Thank you.